There we go. Okay, so remember 2.5 was about mainly marginal cost and marginal revenue and marginal profit and all that jazz. So remember that the marginal cost, revenue, and profit are the derivatives of whatever function you're talking about. And remember, your Y01 is most likely going to refer to them, whoopsies, as MCMR for marginal cost and marginal revenue. They don't usually refer to marginal profit right off the bat. They usually kind of ask you to find it in terms of marginal revenue and marginal profit. Sorry, marginal revenue, marginal cost. But then remember, it's just like regular profit is revenue minus cost, marginal profit is marginal revenue minus marginal cost. And then we did one example where we had to look at essentially the slopes of the cost and revenue function. Because remember, the derivative tells you a slope. Remember, that's super duper important. So derivative tells you slopes, so we could also look at the slopes. Also remember that so we were talking about like whether or not they should make an extra item, and say we wanted to talk about making the 101st item. We did this the other day, but remember, to talk about making that item, making the 101st, you actually want to look at the slopes at 100. So always keep that in mind too, is that if you want to talk about increasing the production by 1 to say the 101st, you actually want to look at the marginal stuff at 100. Parker, hopefully that helped. So we have one more question from 2.5 that we didn't get to the other day. That also is kind of this similar idea of looking at slopes. So we have the graph of the cost function here. And we want to answer the following question. So now I can scroll back down past that because we need the graph in there. So we want to know whether it will cost more to produce the 500th item or the 2000th item. A side note really quick. Like, how can you kind of tell the difference between whether or not they want you to talk about regular cost or marginal cost? If they talk about something like the 500th item, so if it's like a particular item, this is most likely that they're trying to ask you about the derivative, the marginal. Whereas if it talks about something like 500 items, where it's like kind of talking about a range, if you will, it's talking about all of the first 500 items, then that would most likely be referring to just the regular cost. So it does take, kind of got to read it carefully to try to figure out if they're talking about the derivative or the regular. But since they're talking about producing these very particular items, we want to talk about the derivative. Since we don't have the derivative function here, we need to talk about our slopes. Now, again, if I want to talk about producing the 500th item, I technically want to look at the slope at the 499th. Now, these Q values on the axis are in thousands. So 500 would actually, kind of be at 0.5 here. Now, since the 499th item, in terms of this graph, is so obnoxiously close to 0.5 that I can essentially just think about it as a slope at 0.5, or I can just try to say, here's 0.5, take the point obnoxiously close right next to it, and that'll technically be where you want to look at. Now, if this were in, one item instead of thousands, if I wanted to talk about creating the second one, I would have to look at the slope at 1. I'm just trying to say, I mean it when I say that if you want to talk about making the 500th, you have to look at the slope at the 499th. But in this case, on this graph, it's essentially right up at 0.5 because of how this graph is drawn and the scale on the Q-axis. So that's kind of my slope at the 500th, the 499th item. And then I want to compare that to the cost to produce the 2000th. So that would be, right next to 2. So if I take the slope of the tangent line here, and remember, if you're having trouble finding out what the tangent line looks like, while it's not the official way to do it, just take a point really close to the point you want on the function between them. It's not officially the way to do it, but that's a decent way to get a decent approximation of what it would look like. So we have these two lines that we kind of want to compare. Does it cost more to produce the 500th or the 2000th? Well, between those two kind of line segments I've drawn, which one has the steeper slope? And the one on the left does, the one at the essentially 0.5. I'm going to say 0.5 and 2 just for my sanity instead of the 4.999 and the 1.999. But technically it would cost more to produce the 500th item because the slope is steeper than at the 200th. And then I want to ask that same kind of question. Let me do it in a different color. For the 3000th versus the 4000th item. So again, technically I want to look at the slope at the 2999th and the 3999th. But that's essentially at 3 and essentially at 4 on this graph because of how the units are. So 300, 3000th, scroll up. Do you mean down? I think. To get rid of the little. Also try to tap on your screen if it's that kind of option bar that's getting in your way. If you tap your screen, you should be able to make it go away. Is that the direction that you meant, Anastasia? You wanted me to go down technically? Yeah, I can go a little farther. Let me make those lines not crash into each other. There we go. So now comparing those two red lines that I've drawn, which one's steeper, the one at 3 or the one at 4? And again, I'm just saying 3 and 4 for my sanity. Well, the one at 4 is steeper because that one has a steeper slope. So we would say that it costs more to produce 4000th item. Let me try to zoom out and down now. The 4000th item, since again, the slope is steeper. So we don't even necessarily need to know these derivative values to be able to compare them and see kind of whether or not we're making extra profit or not. That's not what this question was asking. That was what the other question was asking. I'm sorry. But in here, we could essentially compare the difference in, the cost of producing a next item. And just by comparing the slopes of this cost function at those certain points that we care about. Questions, concerns on that idea? All right, I'll leave this up for like 10 more seconds. All right, so the next thing I want to do is I want to talk about two types of questions that you have probably already seen on your homework if you've been working on it already. Because while you technically have the tools to do them, you might not necessarily see one thing you need to connect. So I want to talk about them. There's ones that it's something like, I'm pulling it off the top of my head. I don't know, maybe you have that f of 4 is 415 and f prime of 4 is 3 and the second derivative is greater than 0. It usually says something like x is greater than or equal to 4. And then you're asked to estimate or choose the best, choose, I forget how it's exactly phrased, but choose the best estimate for, let's say, f of 8. And then it's technically a multiple choice question. So let me see. 12. Sure. And so these would be your 3 options and you kind of have to pick the best one. So here's what will happen for this one. So in section 2.3, I think, we found that way of estimating, some value based off of the original function and the derivative at a certain point. So we could say that we can estimate f of 8 by taking f of 4 and adding on some of its derivative values. And since the difference between 4 and 8 is unfortunately also 4, we multiply that by 4, and we can get an estimate for where that function is at that point. If we were to do that here, we would get this. So let me make these all estimations. 27. Oh, there it goes. So that might make you think that the answer should be 27, but it's actually not going to be 27. The reason for that is because remember that this process is purely an estimation, and the fact that they give us this extra piece of information here is actually going to help us make a better estimate. So essentially, here's what's happening. Is we don't really know exactly what the function looks like, but we know that, f of 4 is, up here at 15. And essentially what this calculation does is, remember, that's called a tangent line approximation. So it's technically using a straight line to kind of approximate where the function might be. But essentially this extra piece of information we have now about the second derivative is going to tell us a bit more about what the function's actually doing. So essentially, since we know that the second derivative is, let me try to move this up a little bit in case people have that little annoying thing in the way. Seriously though, tap your screen, I think it makes it go away. But anyway, so we know that the second derivative is positive. So remember, second derivative tells us about concavity. So if it's concave up, we know it must look, if the second derivative is positive, we know it must, oh my goodness. If the second derivative is positive, we know it must be concave up. So we know that it must look something like this. And once I got rid of the obnoxious circle and tried to only circle it once, it'll catch up with me eventually. Go. Or not. There we go. Now we also know that the first derivative is positive because it's equal to 3, and 3 is a positive number. So we know that the function must be increasing. So we know that it kind of has to look like that right side of the concave up option. So essentially what that means is essentially my function must look something like this. So if you think about it, this estimation that we get from that tangent line approximation, since the function is concave up, actually ends up being like too small because the function is going to be curving upwards. So actually the best estimation for this would actually be 31. If, for instance, it had been that the second derivative was less than 0, then we'd have concave down, and then it would have been, too big, and the option would have been 23. But essentially what we have here is we can find an estimate using the tangent line approximation. But then because of the fact that we know something about the second derivative, we can tell whether that estimation is too large or too small. So that's a question that comes up on your homework. So now you should have the connections to understand it. You kind of had all the stuff you needed, you just might not have realized how you needed to piece it together. And then there's one more. Can I remember what it's like? Oh gosh darn it. Okay, I remember. Questions on that before I move on to the next one? Okie dokie. All right, so the next one, it's going to be something that's phrased somewhat like, I'm going to write it kind of bullet pointed almost. So we say we have the revenue of selling 99 items is, I don't care, 120, and the revenue of selling 101 items is, I don't know, 170. Estimate the marginal revenue at 100. So essentially what we have here is we have Q values and we have R of Q values. So we have 99 and we have 101. So 120, don't know that, 170. So if you think about what we were doing in 2-1, since we want to estimate r prime of 100, what we would love to do is we would love to take the average rate of change on both sides and then average the two. That's kind of what we did when we were given those set values in that table, is we took kind of those sided average rates of change and averaged them together. We can't do that here because we don't know what the revenue at 100 is. So what we're going to do instead is we're going to do the next best thing, which pretty much turns out to be equivalent. And we're going to take essentially the average rate of change just between 99 and 101. So we'll take our 170 minus 120, 101 minus 99, 50 over 2. Y'all know my arithmetic's bad, but I think that's right. Yeah, 2 to 7 is 5, yeah. So essentially, there's one of like that on the homework. I think it's cost instead of revenue, but the idea is the same. You're essentially given the original function on kind of either side of the thing you want to estimate the marginal one for, and you can just take the average rate of change between the two things that you have, because it's on either side. You have one piece of information on either side of the thing you care about. So if you take their average rate of change, it's kind of a good enough idea. Questions, concerns on that before we go on to our new notes for chapter 3? All righty. Everything else should be doable. I think these were the main two that had kind of possibly missing links that you might not have realized how the things link together. There's lots of ones on there that you'll be using this, maybe not, maybe I shouldn't say lots, but there's a few on there that you'll be using this tangent line approximation idea for, so keep that in mind too, if you're not done it already. But anyway, before we completely move on to chapter 3 notes, I want to talk about your homework for this coming week. Not the one that's due tonight, but the one that's going to be up for this week, because it's going to be the tiniest bit different. And the reason is, if you thought Wiley was bad before, it's absolutely horrendous for chapter 3. So there would be cases in past semesters where people would put in the correct answers. I would put in the correct answer in absolutely any format I could think of, and Wiley wouldn't accept it. So I would have to answer 5 million emails every day, and it was just, I hated it. So I don't do it anymore. So, but you will see that there is a homework on Wiley. So here's essentially what's going to happen is there is some homework on Wiley. It's shorter than usual. It's like 9 questions instead of like 20. And it's the type of questions from chapter 3 that Wiley doesn't hate. The large majority of questions from chapter 3, Wiley plus just decides to hate. I don't know why, but there are some up there, and those will be due like usual. They're going to look slightly different than what we cover in class, but that's because essentially what we're covering in chapter 3 is we're finally getting into the derivative rules. So we're going to actually be able to find these derivative functions fully and actually use the actual thing that we've been wanting to use all along. So essentially the homework on Wiley is going to look very similar to stuff you were doing in chapter 2, but now you get to use the actual derivative to answer them. So there's still going to be things like interpreting, just finding derivative values and all that jazz. But now you're actually going to be able to use the rules. And then what I've done is I've created, it's on Blackboard now, it just popped up right before class. There's this chapter 3 practice. So as it says down here, your official homework is on Wiley. So that date's going to be wrong because I copied this from my other class that has theirs due on Mondays. So yours going to be due on I guess the 13th would make sense. Yeah, so the 13th, so it's officially due on the 13th. But what I'm suggesting is that you do at least a subset of this practice that I've put on here, which is why your Wiley assignment is smaller. Because what we're about to see in class is they're going to look much more like this, where it's just find the derivative of these functions. There's a lot of them, and I'm not saying that you have to do them all, because this is not going to be officially checked. Your official homework is the one through Wiley. but you should really at least do a subset of these. Do as many of them as you need to be able to feel comfortable doing these derivatives. There's a couple challenge ones if you like, if you're good at derivatives and you just want to challenge. And then there's kind of a different set down here. So don't forget about kind of this bottom set down here. If you start going through the first part of it and you're like, oh, I feel good, there's also kind of this second part that's different. But anyway, and since it's not officially being checked, you've got an answer sheet. So all the answers are here. You can check yourself. These ones are on other pages. So I essentially, here's all of the answers in kind of unsimplified form. And then if you scroll down enough, there's like worked out solutions for them. So that's kind of like an extra piece of homework, but again, it's not official, but it's highly, 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 highly suggested. Again, your Wiley homework is shorter specifically because I wasn't trying to make you do double the work, because that would be not cool. But anyway, that's how that's gonna work. So let's get into chapter 3. So chapter 3. Derivative rules. Our notes are going to look a bit different because we don't really have definitions or anything to take down. It's just rules and then doing a bunch of examples until our arms fall off. But that's kind of how you learn derivatives, is you just do 5 million of them until you feel good about it. So, so a lot of these rules are kind of just going to have to be on a trust and believe me basis. I can't really give you the reasoning behind of them. Some of them, like, you can prove why it is what it is, but it's just too high a level for this class. It's almost too high a level for me. I hate them. But anyway, so I'll kind of give you some background about why the rules work for kind of these first two. But after that, it's kind of just trust and believe me. You just use them. Now I'm going to write all of these in terms of Leibniz notation just because it's just easier to write in Leibniz notation. So essentially what I'm going to be writing is something like this. Now this thing right here just means take the derivative. Take the derivative. So if I want to take the derivative of a constant, so just some number c, that's going to be equal to 0. Now, kind of the reason for that, again, I can kind of give you the reason for these first two, and after that, you kind of just got to trust and believe me. Remember that we're working with functions. So if I have a constant function, that's a little too slanted. If I have a constant function, that's just like a straight horizontal line. And remember that the derivative tells you slope. If you haven't gotten that in your head yet, make sure it's in there. Derivative equals slope. I'm even going to write it up here. Derivative is a slope. I can't even write slope. That looks like slip. Slope. I'll even write of tangent line to be extra specific. But a derivative is a slope. So if you have a constant function, well, what's the slope of that line? The slope is 0. So that's why the derivative of a constant is 0. Now say I wanted to take the derivative. I'm talking really fast. I got to slow down a little bit. So I want to take the derivative of a linear function. And say for now we just don't have that plus b, so we just have mx and the b is 0. We'll take care of the other case in a second. So if I have, some linear line that's just, going through the origin. Well, what's the slope of that line? It's whatever m is. So the derivative of some m times x, some constant times x, is just going to be m. And now you got to start trusting and believing. Our next rule says if you take the derivative of a function that is added or subtracted to another function, what you're going to do is you're going to take the derivative of the first function and add or subtract it to the derivative of the second function. So essentially, this is just a super nice rule that tells us that we don't have to do anything special for like a string of things that are added and subtracted together. We just kind of take the derivative of each piece and then add or subtract them together depending on what we started with. And then the derivative of a constant times a function, say you have some constant times a function. essentially what happens is the constant kind of just doesn't do anything, and then we just take the derivative of the function. I'll often say that the constant comes along for the ride. That's usually the verbiage that I'll use. It's just essentially that when you have like this function, the constant doesn't really affect the derivative at all. It just gets multiplied by whatever the derivative of the function is. So those are our first set of rules. So, well, one other thing I'll say is kind of a combination. So say I want to, whoa. So I said the derivative of a linear function without the b, but what happens if we tack on the b? Well, if you just think about this in terms of slope, what's the slope of that line? It's still just m. And this is essentially a combination of all three of these rules together. It's essentially taking that sum and saying, what's the derivative of mx? Well, that's m. And then I have to add that to the derivative of b, which is 0. So technically, this is like m plus 0, which is just m. So that's kind of why it wasn't really written in the original rules, because we kind of didn't need it because it kind of pops out from all the other rules. But anyway. So let's do some examples of kind of these. Ooh, catch up to me. There we go. Kind of these first set of rules. So I'm going to do the first row, and then I'm going to have y'all try the second row by yourself. So say we want to take the derivative, we want to differentiate the function 175. It's just a constant. It is a number. There is no variable there. There's no x next to that 175. So since there's no variable, it's just a number by itself. The derivative of a constant is 0. So f prime of x is just 0. Now with these, since we're just doing example after example after example, I'm going to pause after each one and kind of be checking the chat to see if there's questions. So just pop them in as you have them. I'm not going to like specifically say questions every single time. Otherwise, if I don't see any questions, I'm just going to keep going after I pause for a little bit. So if I go over to 3, I want to take the derivative of this guy. So I have 19 times x. I'm kind of in this mx situation here. So if I have a constant times x, its derivative is just that constant. So our derivative there is just 19. Let me zoom out a little, just in case people still have that thing on their screen. I can't zoom out. There we go. And then let me say I pop over to number 5. Oops, too far. There we go. So I want to take the derivative here. I want to be careful, our variable is now t. So here is where I kind of have to deploy this derivative of the sum and difference rule. So that tells me that I want to look at the derivative of 2 first. So what's the derivative of 2? There's no variable attached to that. It's just a number completely by itself. Derivative of a constant is 0. And then my sum or difference rule tells me that I'm going to add that to the derivative of 6t. Well, that's 6 times just the variable t. So we're going to have that the derivative of that is just 6. So in total, the derivative is just 6. For these ones that we're doing today, and well, tomorrow too, as we're learning these, I should say, I'm going to be doing a lot of intermediate steps. Once you get good at these, I personally would always just jump down to 6. Like once you've been doing these for so long and you've done a million of them and you just see what's going to happen. You don't have to write out 0 plus 6 equals 6. You can just jump straight to 6. So if you want to keep writing 0 plus 6 for the rest of your life, that's perfectly fine too. Whatever. I'm gonna sit here awkwardly for like a minute. And I want you guys to try 2, 4, and 6. It's saying my connection is bad. That's not good. So I'm gonna just sit here awkwardly and try 2, 4, and 6, and then we'll talk about them in a second. Is it still saying my connection was bad? No. Apparently I shouldn't try to, I shouldn't try to teach from home. Apparently I should just go to my office. right, I'll give you like 30 more seconds. These ones are the ones that should hopefully go the quickest. I know some of you are just seeing this for the first time ever in your life, but. I assume you can see now at a stage, and let me know if that's not the case. All right, so number 2, if we want to take the derivative of just the number -2, it's just a number by itself. There's no variable attached to it at all. The derivative of a constant is 0. I'm going to go through these slightly faster because I just gave you some time to look at them. But as I said before, stop me at any time if you have questions. Derivative here, we have essentially -27 times just the variable t, so that would just give us -27. This last one has a tiny trick to it. So we would have to, again, kind of split this up into 2 pieces. What's the derivative of 25x? That's just 25. And then we have to add that to the derivative of pi. What's the derivative of pi? Pi is a number, so that's just 0. 25. So pi is a number. There was no variable attached to it at all, so the derivative of a constant is 0. Oh, I always forget to write this. Well, it's technically in there already, but one thing I'll say, it's technically a special case of this MX rule, but a lot of people, for some reason, really struggle with it for some reason. No, it's fine. But anyway, the derivative of x by itself is just 1, because technically that's 1 times x, so the m there would be 1. But for some reason, there's a disconnect a lot of times, and people forget that one. So I'll write that down as quote-unquote its own separate thing, but it's technically kind of considered in that one. But anyway. So I'll keep that up for 5 more seconds before I scroll down. Any questions, concerns on 1 through 6? Cool. So I'll kind of leave that last row in there. So now we got to talk about this one's kind of our first official rule that kind of has a name. So the power rule tells us that if we want to take the derivative of some variable to a number power, this is going to, you essentially bring the power outside, like in the front, and then you subtract 1 from the power. So you'll often hear me say, bring the power down, subtract 1 from the power. Before I forget to say it, yes, you will have to memorize these rules. Again, doing these, we do so many of them that they should start to just be memorized, but you will need to commit them to memory. Funny side note story, I taught high school a couple years ago, and by that I mean like last year. Anyway, and I taught high school, and when I went over this with them, they decided to lovingly call it the yeet it and drop it. So if that makes you remember how to do it, whatever floats your boat. I think it's weird, but you know, whatever. Other thing I want to note, that's not how you spell. This is a variable to a number, and I make that specification because of the next rule we're going to see on the next page. So this has to be a variable to a number. But anyway, let's see how this works. Let me scroll down a little bit past that section. There we go. So we've got a lot of ones here, but let's, side note. Another side note. Lots of side notes. There's 2 exponent rules that you really want to remember. So if you have a root, and even if you have a power inside of it, this can be rewritten as essentially a fractional exponent. So specifically, if you have like a root, that's going to become a 1 over that root power. So a square root becomes x to the 1/2, a cube root becomes x to the 1/3. And also, if you have 1 over x to a power, you can rewrite that as x to the negative that number power. So we're going to have to use those every once in a while, because to use the power rule, it has to look exactly like this. It has to look like x to a power. It can't look like 1 over x to a power. So, examples. And, whoa, no, don't do that. Zoom back in. Zoom. That's enough. So, let me break this up so that I don't run into my other problems here. So say I want to take the derivative of x to the 8th. My power rule tells me to essentially bring that 8th power out front and then subtract 1 from the power. So we would have 8x to the 7th. And this is, again, where you don't have to write this little intermediate step of actually writing out 8 minus 1. If you just want to jump straight to writing 7, go right ahead. If you want to write out the 8 minus 1, go right ahead. Whatever floats your boat. Anyway. Pause really quick. So then for the second one, we have to rewrite this first, because as it stands, it's not in the correct format. We have 1 over something. We need just x to the something, so we need to rewrite this as x to the -3rd. Now, I need to stress, because for some reason, and it really trips people up, all I've done is rewrite the original function. I haven't taken a derivative yet. So really take those two things and completely separate them. Rewriting things in terms of exponential rules is completely different than taking a derivative. I haven't taken a derivative yet. A lot of people will do the rewriting step and think it's the derivative, and it's not. So anyway, we have the correct format now. This power rule tells me to bring the power down, subtract 1 from the power. So -3x to the -4th. Number 3. Once again, we need to rewrite this. We can't use the power rule yet because we don't know what the power is. Well, we do, we just need to rewrite it. So this is equivalent to x to the 1/2. Again, I haven't done any derivatives yet. I've just rewritten it, into something equivalent. And now that it's in the correct format, I can take its derivative. And we can say bring that power out front. Subtract 1 from the power, so we get 1/2 x to the -1/2. If you like, you can change that back to kind of its original form, or you could write, we're out of space, this way, 1 over 2x to the 1/2. That's a 1/2. It doesn't really look like it. Let me try to rewrite that too. It looks really silly. That's a little better. All 3 of these would be completely acceptable answers. I usually just leave mine in terms of negative exponents, but whatever floats your boat. For questions like these, I rarely ever ask you to simplify them. Triple check my instructions on quizzes or exams, but usually you don't need to simplify them at all, so you can kind of keep them in whatever format you want. Once we get to chapter 4, we do a little bit more with them, so we sometimes need them to be slightly simplified. So you will want to be familiar with them, but you don't necessarily need to simplify them just if you're just generally finding the derivative. Anyway, the next one. So we've got a slightly different thing here because now we've got this 2 out front. We didn't have any constants in the front of our functions before. So what do we do with that? Well, this is essentially that idea of that constant times the function. So that 2 essentially just kind of comes along for the ride, and then we just have to take the derivative of the x to the 4.5. And taking the derivative of that, we bring the power out front, subtract 1 from the power. 2 times 4.5 is 9. Why did I write e? X to the 3.5. For the next one, I don't technically have to rewrite this one, but I'm going to. I could bring it as 1/4 times x squared plus 3. So the reason we had to rewrite 2, but we don't have to rewrite 5, is the position of where the x thing is in the fraction. If the x thing is in the denominator, then you have to rewrite it. if the x is in the numerator, then technically it's just a fraction times that variable. So you don't technically need to rewrite it if you don't want to, but I'll rewrite it like that. So if we wanted to take the derivative, the 1/4 would come along for the ride. Derivative of x squared, bring the power out, subtract 1 from the power. And now we have this plus 3 at the end. So now this is where our sum and difference rule comes in. So we add the derivative of 0. The derivative of 3, which is 0. Because 3 is just a number, no variable attached to it, it's just a constant. So the derivative of a constant is 0. So this would reduce to 1/2 x to the first. But we usually don't write the little 1. But if you want to, go right ahead. I'm going to, again, sit in awkward silence while you try 6 and 7, and then we'll go over 8 and 9 together. So I know 7 looks slightly longer than the ones we've done, but it's kind of like 5, just with 2 extra pieces. So try 6 and 7. I will give you a minute. All right, so for 6, whoops. -3 came along for the ride, bring the power down, subtract 1 from the power. You should get 12x to the -5th. And then on 7, we just have to take the derivative of each piece separately. So bring the power down, subtract 1 from the power. 2 comes along for the ride, bring the power down, subtract 1 from the power. Derivative of 5x is just 5. Derivative of 4, I'm running out of space, is just 0. So if we wanted to rewrite this, we would have 4x cubed plus 6x squared plus 5. All right. So number 8, we have to rewrite this first as x to the 1/3 plus x to the -2nd minus 5x, because they're not in the right format yet, so we can't use the power rule on those first 2 pieces without rewriting them. Once we rewrite them, have done nothing in terms of derivatives yet, so now we want to go about taking the derivative. Bring the power out front, subtract 1 from the power. Add that to the derivative of x to the -2nd, bring the power out, subtract 1 from the power. Minus the derivative of 5x. The derivative of 5x is just 5. Reducing that a little, we get 1/3 x to the -2/3 minus 2x to the -3rd minus 5. And you could rewrite those, change those negative exponents into positive exponents by putting them in a denominator, or you can just leave it as is. And the last one for this section is x to the pi. Pi is a number, so this is the correct format that we need to use the power rule. So bring the power out front, subtract 1 from the power, and we kind of just have to leave it as pi minus 1, but that would be our derivative. Questions, concerns on any of those before we move on to a different set of rules? I will stress these rules build upon themselves, so you don't want to wait until the very end to start realizing that you don't know why things are happening the way they are. We won't get to any of the super fancy rules today. That'll probably be Thursday, but some of the rules that we'll get into later rely on you using these rules really well. Please stop that. Stop. Shush. Other reason I should go to my office. So if you have questions, please ask them as soon as you have them. Don't wait until the very end. They can be able to hear you, you jerk. All right, so I don't see any questions, so we'll move on. Just some more rules. Can y'all hear that? A little scratching? Because if so, I'll kick her out, but all right, no one's telling me they can hear it, so hopefully you can't hear it. My cat's being a dork. All right, so some more rules. So we want the derivative of some a to the x. So this is why I made that specification before, because this is going to be a number to a variable. Two completely different cases, completely different rules. So if I want to take the derivative of, say, a number to a variable, this one's honestly probably, in my opinion, this is the worst rule. But there's also a very special case of this rule that we are going to use way more often. And that's the derivative of e to the x, because remember, e is a number. You will never see me or essentially any other person in this math department use e as a variable. Whenever you see e, it's going to be the number. So the derivative of e to the x is just e to the x. This one is the one you're going to want to focus on for like quizzes and exams. Yes, I said that you should be memorizing these, but to be honest, I personally almost never use this rule. We'll use this rule in the examples below, but after that, it's much more often that we use the e to the x rule than the a to the x rule. So take solace in that, I guess. But anyway, and then if we want to take the derivative of some e to the kx, where k is just a constant here, this is going to be, you essentially bring that constant out front and then have e to the kx again. Now I also need to talk about this rule too. So I don't know why your book presents this rule right now as kind of its own separate piece, but I'm trying to follow your book so that if people look back at it, it's not different. This is technically a chain rule. Now, if you've never seen derivatives before in your life, you don't know what chain rule is yet, but eventually you will. And once we get to chain rule, I'm going to stress about 5 million bajillion times that this was a chain rule. So while we're using this rule right now, once we get to chain rule, we almost want to forget about it. Because what will happen is a lot of people will think that they need to use the chain rule again when they don't. And again, I'll talk about this again when we get to chain rule. But anyway, we do have this rule where if you have some e to the constant times x, you can bring that constant out front and then just kind of rewrite that whole entire e to the kx again. And then if we want to take the derivative of the natural log of x, this one's probably the strangest because it changes the format the most. All of the other ones, they kind of have a similar format to their derivatives. This one, the derivative of the natural log is 1 over x. So it kind of has nothing to do. Doesn't look like the natural log at all. But anyway, so those are our next 3 rules that we're going to use for this next set. Let's see, we've got 25 minutes. So we're going to go, the way we're going to do this is we're going to do the first column first, because I want to get to kind of problem 3 and problem 4 below it. And we'll just get as far as we can, but we're going to do the first column first. So let's say we want to find these derivatives. Let me, again, split this up so I don't go too far over. So if I want to find the derivative of number 1, first thing I need to take is the derivative of 2 times 3 to the x. Please, for the love of all that is good and holy, do not make that 6 to the x. That's not how that works. The one thing has an x, the other thing doesn't. You can't combine them together. That has to stay 2 times 3 to the x. So essentially what happens here is that 2 just kind of comes along for the ride because it's a constant times that function. And then the derivative of 3 to the x is our natural log of 3 times 3 to the x. And then we have to add on the derivative of 5e to the x. That 5 comes along for the ride. Derivative of e to the x is e to the x. And actually, you can't really simplify that at all unless you wanted to punch 2 times the natural log of 3 into your calculator and write down the decimal. I would just leave it as it is. You can't really combine anything together here. Pause.
I have a question. Why doesn't the 2 become a 0? Like when we take the derivative, because it's a constant.
So it's attached to that 3x via multiplication. So since it's multiplied to a function that has an x in it, it doesn't go, the only time, so, okay. So the things that were kind of disappearing, if you will, the ones that have the derivative of 0, is when we had something like +2 or +7 kind of tacked on the end, where it was just the number by itself. But since this 2 is attached to a function with multiplication, it has to stay. So the only time the constants are going to become 0 is if it's a constant completely by itself after an addition or subtraction symbol, and it's not attached to another function in multiplication in any way. If it's multiplication, then it has to stay. If it's addition or subtraction, that's when we have that the derivative is 0.
Okay, that makes sense. Thank you.
Also, really good question, because lots of people trip up on that. All right, so 2. We want to take the derivative here. Derivative. What's the derivative of e to the x? It's e to the x. That's like everyone's favorite rule because it just stays the same. Or maybe it's the worst rule because it doesn't change. I don't know. Anyway, now I'm getting to the babbling point in my life. Derivative of 2 to the x becomes natural log of 2 to the x. And here, this is where we have now +7. That 7 is not attached to anything that has an x in it. It's not multiplied by anything that has an x in it. It doesn't have an x attached to it at all. That's just a constant by itself, so its derivative is 0. And you can always just not write the +0. I don't think you always have to tack on the +0. Again, I'm kind of writing this out in very full generality just because it's new to some people. But once you get good at these, if you want to start just writing the final answer, you totally can. I'm going to try to tack this last one in while keeping those rules up there. So if I want the derivative here, I need the derivative of 8x squared. So that 8 comes along for the ride. Derivative of x squared, bring the power down. Subtract 1 from the power. Add that to the derivative of 8e to the x. The 8 comes along for the ride. What's the derivative of e to the x? It's pen is going to stop working. It's e to the x. Lots of 8's in this one. Then we have to add that to the derivative of 8 times 4 to the x. Since that 8 is multiplied to something with an x in it, has to stay along for the ride. What's the derivative of 4 to the x? It's natural log of 4 times 4 to the x. So now that I don't need the rules anymore, I can scroll down a little bit. So we could, of course, rewrite this one, 16x plus 8e to the x plus 8 natural log of 4 to the x. Side note, if this was just 8 times 4 to the x, make sure you put the, well, you could write it a couple different ways. You can either write that kind of multiplication symbol, or, you know, you could put one of them in parentheses, whichever one floats your boat. Just make sure that you do not write just, you know, that and think that I'm going to think that those are multiplied together and not just 84 to the x. So be really careful when we have these a to the x terms. You need to split it up and make sure it remains separated in a way that I know it's separated. Anyway, but since there's kind of that natural log of 4 in the middle, the natural log, the fact that it's a completely, you know, that natural log piece is kind of what makes it separated, so I didn't need anything else there. But anyway. So now I want to go on to problem 4. Again, I want to do the first column just for time's sake, so we at least get some of them in, and then we'll go back to any ones we miss on Thursday. So I know I kind of have to go past the rules, but hopefully you have them kind of in front of you, so you'll be able to use them. So I want to take these derivatives as well. Now we've got some natural logs floating around in here. So if I want to take the derivative here, derivative of 5 natural log of t, 5 comes along for the ride, times the derivative of the natural log of t, which is 1 over t. Add that to the derivative of 7e to the t. 7 comes along for the ride. What's the derivative of e to the t? It's e to the t. Subtract the derivative of 4t squared. The 4 comes along for the ride. Derivative of t squared, bring the power down, subtract 1 from the power. Subtract the derivative of 12. 12 doesn't have a variable attached to it. It's not multiplied by something that has a variable in it. So the derivative of a constant is just 0. We can rewrite this if you want. We could make it 5 over t. You could leave it as 5 times 1 over t if you want. Plus 7e to the t minus 8t to the first. I always suggest at least simplifying the power rule ones. But if you want to leave like it as 5 times 1 over t or something like that, that's perfectly fine. The next one. I just want to stress one more time. Feel free to ask questions as you have them. The other thing about this with me is I've been doing these derivatives for so long. Without sounding condescending, I've gotten so good at them that sometimes I forget what it's like to not know how to do them. So if you need me to slow down or try to reiterate something or re-explain it, please let me know. So derivative of this one, we need the derivative of 160. There's no variable attached to it. It's not multiplied by anything with a variable in it, so that's just a constant, so its derivative is 0. Plus the derivative of 3t squared. 3 comes along for the ride. Bring the power down, subtract 1 from the power for the derivative of t squared. Subtract the derivative of 2t, which is just 2. Oh, I should say that. I'll say that in a minute. I'll get that to the second. Let me just finish this one really quick. And then the derivative of 2 natural log of t. 2 comes along for the ride. Derivative of natural log is 1 over t. So I can simplify this a little bit if I would like to. I would write it as 2 over t, but whatever floats your boat. So Brianna, you asked me why in the one before this I separated with a multiplication dot the 4 and the 2, but not the 7 and the e. I could have totally put a multiplication dot there. The reason I don't have to, I guess maybe if I was being consistent with the 7 comes along for the ride and then the derivative of e to the t is e to the t, I should have been consistent and put that multiplication dot there. I will say though that in general, it's not necessary between a 7 and an e because you kind of recognize that the e is separate from the 7. But say I wanted to write 4 times 2, but I just wrote it like this. Like that to me says 42, not 4 times 2. So I need to somehow separate them as either 4 times 2 or 4 times 2. So that's why I needed it there and why it showed up there. If I was being consistent, and I should have been, I probably should have put that multiplication symbol between the 7 and the e. In general, it's not needed because it's separated enough because the e is so separate. But I'm starting to get lazy. All right, let's just keep chugging. Number 3. Ooh, this one has a tiny bit of a trick to it. And nudge, nudge, wink, wink. It is a trick that I like to use a lot. So for the derivative of this one, notice that this first thing that I need to take the derivative of, the 4e to the third, there is no variable in that. Remember, e is a number. So that's a number times a number to a number. This is just a number. There's no x, well, in this case, sorry, it would have had to be a t. There's no variable in there. That's just a constant. The derivative of 4e to the third is 0 because it's a number. I like to do that a lot. Nudge, nudge, wink, wink. And then for the derivative of 2.45 times the natural log of t, that 2.45 comes along for the ride. And I'll bring in my multiplication symbol. And then the derivative of natural log of t, 1 over t. So if we want, we can rewrite this as 2.45 over t. Questions, concerns about any of those? We've got 15 minutes, so I'll probably go up and do the second column of that first problem because it's got some of the e to the kt's that we haven't talked about yet. And then that'll probably be all the time we have. What is up? I see a hand. David?
Oh, I'm not sure if you already mentioned about this. So we're not going to worry about 4, 5, and 6 for problem 3.
So I think that's what I'm going to go back and do right now. I was trying to get this whole first column done just because the other column on the other one didn't have the natural logs. So I wanted to kind of talk about ones with the natural logs in it before going back. But that's probably what we're going to do right now is we're going to go back up and we're going to get those.
Okay, that worked. Thanks.
All right, so let's do that. Let's scroll back up and get 4, 5, and 6. And now we can bring our rules back in. Yay! And then, so then we'll hit 4, 5, and 6 for problem 4, probably on Thursday. That'll probably have to wait, but we will get to them eventually. All right, so number 4 on problem 3. So I want a derivative here. Derivative of 5. There's no variable there. It's not attached to anything that has a variable in it with multiplication. So it's a constant by itself, so its derivative is 0. Plus the derivative of 3x squared. 3 comes along for the ride. Derivative of x squared, bring the power down, subtract 1 from the power. Once again, if you just know that that's going to reduce to 6x, just do it. If I was doing these on my own, I would just write 6x and not write all this hoopla. But whatever floats your boat, however much kind of extra pieces you need. And then 7e to the negative 0.2. So that 7 comes along for the ride. So we haven't done one of these e to the kt yet. So that's kind of we haven't looked at one of these yet. So that k value is negative 0.2. So what our rule tells us to do is to bring the negative 0.2 down. But then maybe I should avoid saying down because that makes it sound like it's not going to show up again. We write that value out front and then completely leave the e to the kx alone as well. So if I wanted to simplify this a little bit, I could reduce it to 6x. Oh crap, I forget. I think that comes out to be 1.4. I don't have my answers in front of my face because I was like, oh, I can do this. But I'm pretty sure that reduces to 1.4. Yeah, 1.4. I should be able to do that in my head, but. Alrighty. Wait, what about the negative 7? I'm confused about where you're talking about it. So at first we have to keep it along for the ride because the negatives, you got it? So I multiplied the negative 7 and the negative 0.2 to get 1.4. Okay. So next one. 15 comes along for the ride. Derivative of e to the 1/3 x. We're in the same e to the kx case, so that 1/3 gets written out front, but then the e to the 1/3 x completely gets rewritten. Subtract off the derivative of 17x, so subtract the derivative of 17x. The derivative of 17x is just 17. So we can reduce this. 15 divided by 3 is 5. E to the 1/3 x minus 17. And then this last one, let me just scroll down past that because I don't need it. Derivative here, 2 comes along for the ride. Derivative of e to the negative 1.9x, the negative 1.9 kind of comes out front. I'll tack it in parentheses as well. That's not really needed because I have the multiplication dot there, but just for giggles, I'm going to put it in parentheses too. Minus the derivative of 14. That 14 does not have a variable attached to it. It's just a 14 by itself. So it's going to be 0. If I multiply the 2 and the negative 1.9, I get negative 3.8. E to the negative 1.9x. And the minus 0 just doesn't need to get rewritten. Whew. Oh, we still got 10 minutes. So, questions on that before I figure out what I want to do in these last 10 minutes? All right, I think what I want to do is I want to leave these 3 for the warm-up on Thursday, because these ideas, everything we have just covered, so not the things we're about to talk about, but the things we just covered, is going to be essentially what your quiz is going to look like on Thursday. So I'm going to leave this 4, 5, and 6 as the warm-up for Thursday. And I want to jump down and I want to start building up to the next rule. The next rule is, honestly, I don't want to freak anybody out by saying it's the hardest, but it kind of is. It's weirder to get your head around because it's kind of like a rule that tells you to use other rules. So we'll come back. We will do this 4, 5, and 6. We'll just do it on Thursday as our warm-up. So I want to kind of go down here and start talking about the chain rule. We won't really be able to get into it into a lot of detail, but we'll start. So the first thing I want to do is kind of review a concept about compositions. So we talked about compositions way back when in 1.8. And I forget, there was one of my classes that didn't get to the breaking up part and the other ones did, and I forget which one was which. But anyway, so say we kind of review that concept where we have these 2 functions and these are compositions. This is one function inside of another function. And say I wanted to try to break it up. So we had inside functions and outside functions for compositions. And this is going to be where it kind of comes back and bites us in the butt because we need to be really, really good at being able to recognize an inside versus an outside function. So in part A over here, we have the natural log of 3t. So essentially what I want to do is I want to break this up into 2 different functions such that I'm essentially going to replace something in here with z and then say what I let z be equal to. So if we think about what's happening here, we're taking 3t and we're plugging that result into the natural log. So say I asked you to plug in 1 here, you would have to multiply that 1 by 3 and then take that result and plug it into the natural log. So the outside function here would be the natural log. So essentially we could say that this is equal to some natural log of z, or in this case z is equal to 3t. So essentially if I, went backwards and plugged them back in, I'd get what I'd started with. So essentially our outside function here was natural log of something, and then our inside function is 3t. Whereas in this other one, we have 5 times 2t plus 3 all squared. So if I want to try to break this up into 2 pieces, the main thing that's happening here, so again, when you're trying to figure out inside versus outside, one tip I suggest is pretend you're plugging in a number. So say I said let t be 0. What would you do here? If you had to take like each step individually, first thing you would have to do is multiply it by 2. Then you'd have to add it to 3. Then you would have to square that result, and then you'd have to multiply that result by 5. So the last thing you kind of did was multiply it by 5, but you multiplied that squared value by 5. So we would say our outside function, because it needs to have a variable in it, so it can't just be 5. We're going to take our outside function to be 5z squared, and our inside function is going to be that 2t plus 3. So this would be our outside and our inside. So we need to be really good at recognizing when one function is inside of the other. And I'm going to give us a couple tips. We probably won't get that until whatever. Oh, crap. Oh, man. I'll fix that in a minute. What was I saying? Tips. We probably won't get to the full tips until Thursday. maybe today. Anyway, but I'll try to give you some tips and tricks of finding the outside versus the inside function because it's that important to this rule. So I think I'll only have time. I'm going to present the rule and then I'm going to do question 1. Hope y'all don't freak out too much. And then we'll talk about it more on Thursday. So our chain rule, if we want to take the derivative of a composition, now I'm going to write this. I started with Leibniz notation and now I'm going to jump over to Newtonian because the other side of this is easier to write in Newtonian. And let me just write it out and then I'll say it in words. How would you even write that in Leibniz? Oh, yeah, no, the Leibniz notation for that would be super gross. If you're curious, it would look like something like this. Well, no, that would have to be a z. F of z, where z is equal to g of t. Crap, I ran out of space. Times the derivative of g of x. That should have been an x, not a t. So as you can see in the very cramped spot over here, the Leibniz notation is horrible, so let's just erase that. So essentially what this is saying is take the derivative of the outside, evaluated at the inside, evaluated times the derivative of the inside. Oh, can I squeeze it? Yes. 3 minutes. You know what? I'm going to go over problem 1, but then we're going to go over it again on Thursday. But just to give you an idea of how this is going to go, just so that I don't leave it at the rule and not show you how it would work. So again, this one's the hardest one to wrap your mind around because it's kind of rules inside of rules. Jamie, the quiz is essentially on the stuff we did right before chain rule. So all of the things that kind of look like this are completely fair game. And it's just going to be find the derivative. That's all your quiz is going to be on. It's just find derivatives. So say I want to look at number 1. And again, we'll go over this again on Thursday. But we kind of have the inside function being this 4t squared plus 1, and the outside being some, z of, like a z to the 7th. You'll hear me with this chain rule a lot say something to the 7th. So essentially what we have here is like something to the 7th power. So what the chain rule says is since that outside function is z to the 7th, what's the derivative of z to the 7th? You would bring the power down and you would subtract 1 from the power, right? Now notice I left a space in there. So the chain rule says take the derivative of the outside. So I've just done that. I've essentially have something to the 7th power. So I bring the power down, subtract 1 from the power. You evaluate it at the inside. So essentially that inside section is going to stay itself for right now. And so that essentially takes care of this first part. And then we have to multiply it by the derivative of the inside. So the inside function was 4t squared plus 1. So what's the derivative of 4t squared plus 1? Well, that would be 8t, if I can kind of reduce at the same time. So it would be 4. When you bring that power down of 2, that would reduce to 8, t to the first, and then plus 0, because the derivative of 1 is 0. So the derivative here, which again, I'm going through semi-fast because we're out of time, but I'll go through again on Thursday, would be this. So the chain rule kind of takes the rules that we already have and kind of makes them work inside of each other. So that one's going to take a bit of time to get your mind around at first, possibly. But what am I saying? That's the idea behind it. We'll go over it in a lot more detail on Thursday. As I've already kind of said, your quiz will essentially be kind of these first 2 pages. So mainly stuff that kind of looks like this, because this kind of encompasses all of the rules from page 1 and page 2. So that's why I'm also leaving these last 3 for the warm-up on Wednesday, because that will prepare you for your quiz. So we are officially done. If you have any questions, feel free to stick around. Otherwise, have a good day, and I will see you on Thursday. So yeah. Let me stop the recording.